Imagine staring into the night sky, your eyes tracing the countless stars scattered like glitter across the darkness. Now picture one of those stars, tiny, dense, and eerily quiet, suddenly sending out a signal so strange, so inexplicable, that it stops astronomers in their tracks. That's the reality of white dwarfs, the fading embers of dead stars, and the bizarre messages they're broadcasting across the cosmos. These signals don't just puzzle scientists, they defy everything we thought we knew about the universe. And today, we're diving deep into 25 of the most mind-bending, unexplained transmissions from these stellar ghosts. What makes these signals so baffling? White dwarfs are supposed to be in their final act, cooling slowly into cosmic oblivion. Yet somehow they're behaving in ways that shouldn't be possible. Some pulse with rhythmic energy like interstellar lighthouses. Others emit bursts of radiation that appear and vanish without warning. A few even seem to carry patterns, hints of something deliberate, something almost intelligent. Are we picking up echoes of natural phenomena we don't yet understand? Or could there be something out there, something beyond our current grasp, sending these cosmic whispers our way? This isn't just about scientific curiosity, it's about the thrill of the unknown. Every unexplained signal is a crack in the door of our understanding, a chance to glimpse something extraordinary. As we unravel these 25 mysteries, you'll see why white dwarfs have become one of astronomy's greatest enigmas. From strange radio waves to flickering X-rays that vanish before we can study them, each discovery pulls us deeper into the question, what's really happening in the silent depths of space? Buckle up, because by the end of this journey, you'll never look at the night sky the same way again. The first signal that sent shockwaves through the astronomical community came from a small, unassuming white dwarf roughly 1,300 light-years away. Designated as G117-B15b, this ancient stellar remnant should have been quietly fading into darkness, but instead, it began pulsing with eerie precision. Every 1.37 minutes, like clockwork, it emits a burst of X-rays, a rhythmic flicker that defies conventional stellar behavior. Astronomers first detected this pulsating anomaly in 2016. And to this day, no one can fully explain why it behaves this way. White dwarfs aren't supposed to pulse, at least not like this. When stars like our Sun exhaust their nuclear fuel, they collapse into dense, Earth-sized cores, slowly cooling over billions of years. Any variability in their light usually comes from surface vibrations or orbiting debris. But this is different. The signal's regularity is too precise to be random turbulence, and its X-ray emissions suggest something far more energetic is happening beneath the surface. Some researchers speculate it could be caused by a hidden magnetic field, twisting and reconnecting in ways we've never observed. Others wonder if the white dwarf is consuming stray material from an unseen companion, creating periodic bursts as it feeds. Then there's the most tantalizing possibility. What if we're seeing the fingerprints of an entirely new type of astrophysical phenomenon? The signal's clockwork rhythm has drawn comparisons to pulsars, neutron stars that beam radiation at predictable intervals. But pulsars spin rapidly, powered by their extreme rotation, while white dwarfs rotate much more slowly. So how could this one produce such a steady pulse? One radical theory suggests it might be harboring a solid crystalline core, vibrating like a struck bell under unimaginable pressures. Another even proposes the influence of dark matter interacting in ways we can't yet model. What makes this mystery so gripping isn't just the unanswered questions, it's the implications. If a white dwarf can behave this unpredictably, what else might we be missing in the cosmos? Every time this distant star pulses, it's not just sending energy, it's sending a challenge to our understanding of the universe. And as astronomers keep listening, one thing is certain: this won't be the last time the stars surprise us. The second signal takes us even deeper into the unknown, a white dwarf designated as WD 1143-018, located roughly 2,500 light-years away in the constellation Virgo. Unlike the steady pulse of our first mystery, this one behaves more like a cosmic alarm clock, erupting in sudden, repeating bursts of radio waves every 128 days with chilling precision. What makes it so extraordinary isn't just its regularity, it's the sheer intensity of the bursts, each one unleashing more energy than our Sun emits in an entire week. Most cosmic radio bursts are fleeting millisecond-long blips from neutron stars or random, one-off events, but this repeats like clockwork, and its structure defies natural explanations. When astronomers first detected the pattern in 2019, they initially thought it might be a magnetar, a highly magnetic neutron star known for sporadic outbursts. But magnetars don't operate on such strict schedules, and their bursts are far more chaotic. This signal's discipline is almost unsettling, as if something or someone is turning a cosmic switch on and off. Natural explanations aren't entirely off the table. Some theorists suggest it could be caused by a dense asteroid belt or a planetary debris field circling the white dwarf, with chunks of material periodically plunging into its surface and igniting electromagnetic fireworks. Others propose a binary companion, a faint, fast-spinning neutron star, whose magnetic field interacts with the white dwarf in a way we've never seen before. The problem: no such companion has been detected, and the energy output still doesn't quite fit known physics. Then there's the elephant in the room: could this be artificial? The idea isn't as far-fetched as it sounds. The signal's strict periodicity mirrors what we might expect from a directed beacon, a deliberate transmission designed to stand out against cosmic noise. If it were natural, why hasn't anything like it been observed elsewhere? Prominent astronomers have cautiously floated the possibility of extraterrestrial megastructures, like a massive energy harvesting array or a communication relay, though most stress that extraordinary claims require extraordinary evidence. But here's the twist: the bursts aren't identical. Each eruption varies slightly in intensity and structure, complicating both natural and unnatural theories. If it's artificial, why the inconsistencies? If it's natural, why the clockwork timing? This paradox is what keeps scientists hooked. Every new observation peels back another layer, revealing a phenomenon that refuses to fit neatly into any box. Whether it's an undiscovered stellar process or something far more profound, one thing's certain: the universe is forcing us to rethink what's possible. And for now, this enigmatic white dwarf holds its secrets tight. Signal 3 shatters expectations in the strangest way possible by saying nothing at all. Designated J0857+0343, this white dwarf defies logic, not with bursts or pulses, but with an eerie, deafening quiet. While most dying stars emit some form of electromagnetic chatter, X-rays, radio waves, even faint ultraviolet glows, this one sits in near total silence. It's as if the star has been muted, its final whispers swallowed by the void. Astronomers first noticed this anomaly when cross-referencing data from multiple telescopes, only to realize they were staring at a cosmic paradox: a white dwarf radiating visible light, yet producing none of the secondary emissions that should accompany it. This absence isn't just puzzling, it's revolutionary. Current models predict that even the calmest white dwarfs should leak trace amounts of high-energy radiation, especially if they're still warm enough to glow visibly. Think of it like a campfire. You'd expect not just light but also heat and the occasional crackle. J0857 gives us the light without any of the expected noise. It's a stellar mirage, challenging the very tools we use to study the cosmos. Modern detectors are fine-tuned to pick up specific electromagnetic signatures, but what happens when the universe refuses to follow the script? Theories attempting to explain this silence range from the mundane to the extraordinary. One camp suggests an unusually thick, cold atmosphere surrounding the White Dwarf, absorbing all higher energy emissions before they can escape like a cosmic soundproof room. Another proposes that its magnetic field is structured in a way that traps radiation internally, preventing it from reaching us, but the most radical idea. This might be our first glimpse of a white dwarf transitioning into an entirely new state of matter. Some simulations predict that under extreme pressures and temperatures, the star's core could crystallize into a lattice so dense it suppresses energy release entirely. Then there's the unsettling alternative. What if we're not seeing silence, but a signal we're incapable of detecting? Just as humans once lacked the technology to observe radio waves or gamma rays, could this white dwarf be communicating in a language of particles or forces we haven't yet discovered? The implications would rewrite textbooks. Either way, this silent scream forces us to confront a humbling truth. The universe still holds phenomena we don't just fail to understand, we fail to even perceive. And that makes it one of the most thrilling mysteries of all. Signal 4 doesn't just break the rules, it rewrites them on the fly. Meet the frequency drifter, a white dwarf whose transmissions slide up and down the electromagnetic spectrum like a cosmic radio dial stuck between stations. Officially catalogued as L86-422, this star doesn't just emit signals, it warps them, sending out waves that unpredictably shift pitch over days, sometimes even hours. One moment, it's broadcasting in low, rumbling radio frequencies. The next, it's squeaking into high-energy X-rays before plummeting back down again. This isn't just unusual, it's unprecedented. Stellar remnants aren't supposed to behave like this. Their emissions, even when variable, typically follow predictable patterns tied to rotation, magnetic fields, or interactions with nearby objects. But this is chaos dressed as a signal. The first clues emerged in 2021 when a team analyzing archival data noticed something bizarre. The white dwarf's radio emissions weren't just fluctuating in intensity, they were changing frequency entirely, as if the star itself couldn't decide how to communicate. At first, astronomers suspected instrumental error or interference from passing cosmic debris, but repeated observations confirmed the pattern was real. The shifts weren't random noise, they followed a strange, almost algorithmic rhythm, like a malfunctioning metronome. Theories to explain this phenomenon range from the plausible to the borderline fantastical. One leading hypothesis suggests the white dwarf is locked in a gravitational tango with an invisible companion, perhaps a rogue planet or a brown dwarf, whose erratic orbit distorts the star's magnetic field, twisting its emissions into a sonic roller coaster. Another camp argues for an internal explanation. Turbulent plasma currents beneath the surface, sloshing like water in a spinning bucket, could be modulating the outgoing radiation. But neither theory fully accounts for the sheer speed of the shifts. Natural processes usually unfold over longer timescales, not in abrupt, head-snapping jumps. Then there's the outlier possibility: resonance. Some researchers speculate the white dwarf might be acting like a colossal tuning fork, vibrating at frequencies that interact with the fabric of space-time itself. If true, it would imply the existence of phenomena we've only theorized, like quantum gravitational waves or exotic matter states. Skeptics counter that such claims veer into speculation, but the data refuses to conform to tidy explanations. What makes this mystery so gripping is its defiance of categorization. Most cosmic anomalies fit somewhere on the spectrum of known physics, even if they stretch its boundaries. The frequency drifter, it feels like a glitch in reality's code, a reminder that the universe still holds puzzles we haven't even learned to name. Every time its signal warbles, it's not just challenging our models, it's daring us to dream bigger. And in that audacity lies its greatest gift, the thrill of the unsolved. Signal 5 bends the rules of physics and our perception of space itself. Nicknamed the echo effect, This transmission from White Dwarf K072-053 doesn't just reach us directly, it arrives in staggered waves like a voice bouncing between unseen canyon walls. But here's the catch, there are no walls. Telescopes have scanned the region for light years in every direction, finding no nebulas, galaxies, or dust clouds dense enough to reflect the signal. Yet every 8 hours, like clockwork, the star's radio pulses repeat delayed, distorted copies trailing the original by precisely 47 minutes. It's as if the cosmos itself is folding space to create phantom mirrors. The enigma deepens when you consider what it would take to produce such an echo naturally. Ordinary cosmic structures like interstellar gas would scatter the signal chaotically, not return it with crisp, predictable timing. Even black holes, notorious for warping light, can't explain the effect without leaving other observable traces. That's led some astronomers down a far more speculative path. Dark matter. Could invisible halos of this mysterious substance, clustered in specific formations, act as cosmic reflectors? Simulations suggest certain exotic dark matter particles could, in theory, interact weakly with electromagnetic waves, just enough to bounce them like a faint radio mirror. But proving it, that's another story. Then there's the spine-tingling alternative, spatial topology. The universe might not be as smooth as we assume. Theoretical models allow for unseen wrinkles in space-time, leftover distortions from the Big Bang or higher dimensional folds that could redirect signals like a funhouse mirror. If true, these echoes aren't just curiosities, they're glimpses into the hidden architecture of reality. What makes this signal so mesmerizing isn't just the mystery, it's the implications. Every echo is a potential roadmap to forces or structures we've never detected. And as astronomers chase these ghostly reflections, one truth becomes clear: the universe isn't just speaking to us. It's whispering secrets in a language we're only beginning to decode. Signal 6 throws us into the heart of a cosmic partnership gone rogue, a white dwarf locked in a gravitational embrace with another star, yet behaving in ways that defy every textbook on binary systems. Officially catalogued as WD202-465, this stellar duo should be a predictable dance of energy exchange, mass flowing from the larger companion to the dense white dwarf, creating steady X-rays or periodic outbursts. But instead, something far stranger happens. The system emits radio waves in bizarre, synchronized bursts, never when the stars are closest, never when they're farthest apart, but always at the exact midpoint of their orbit, as if some unseen hand flips a switch. Binary systems are supposed to follow rules. When two stars orbit this closely, tidal forces and magnetic interactions leave clear fingerprints, heated accretion disks, predictable flares, or even nova explosions. But WD202-465 laughs in the face of convention. Observations show its companion is a run-of-the-mill red dwarf, far too small and cool to explain the radio fireworks. Even stranger, the signal's intensity doesn't match any known binary behavior. It's not the steady hum of material transfer or the erratic spikes of stellar flares. It's a precisely timed, ultra-sharp pulse lasting exactly 12 seconds, repeating every orbit like a cosmic metronome. Astronomers first noticed the anomaly when radio telescopes picked up the bursts while studying unrelated phenomena in the same patch of sky. At first, they dismissed it as interference until follow-up observations revealed the uncanny orbital synchronization, the leading theory, a magnetic slingshot effect. As the stars swing around each other, their magnetic fields might briefly reconnect at the orbit's midpoint, channeling vast amounts of energy into focused radio beams. But here's the hitch: models suggest this should also produce X-rays and distort the companion star's light, neither of which appear. The absence of expected side effects has spawned wilder ideas. Could the white dwarf's intense gravity be warping space-time just enough to create a natural particle accelerator at that exact orbital phase? Or is the companion star hiding an ultra-dense, undetected object, a neutron star or black hole lurking in its shadow? The most unsettling possibility, the signal isn't natural at all. The precision echoes artificial designs like a navigation beacon or a failed alien engineering project silently cycling through its protocols. Yet the truth might be simpler and more profound. What if we're witnessing a rare phase of binary evolution, a fleeting moment where stellar physics behaves in ways our models haven't predicted? Every pulse from this system isn't just a mystery, it's a masterclass in cosmic humility, reminding us that even the most familiar celestial partnerships can still surprise us. And as long as signals like this keep cracking the sky, our understanding of the universe remains gloriously incomplete. Signal 7 doesn't just whisper, it speaks in riddles. Dubbed the Cosmic Morse Code, this transmission from White Dwarf H0945 plus 240 pulses in a sequence so precise it feels deliberate. Short bursts, long holds, rhythmic gaps, patterns that echo the structured cadence of human communication. Discovered in 2022 during a routine survey of deep space radio emissions, this signal stood out immediately. Most stellar remnants produce noise, static, or at best irregular flickers, but this had the eerie cadence of a language. At first glance, the pulses resemble something a dying star shouldn't be capable of. A repeating loop of 3 quick clicks, 2 prolonged tones, and a silent pause lasting exactly 4.7 seconds before restarting. The cycle repeats every 11 minutes, never deviating by more than a fraction of a millisecond. Astronomers ran the data through every known filter, checking for interference from satellites, atmospheric distortion, or even glitches in the telescopes themselves. Yet the pattern held. Nature rarely creates such disciplined rhythms without a clear mechanism, so what's driving this one? The leading natural explanation points to magnetar-esque behavior. Magnetars, neutron stars with monstrous magnetic fields, are known to emit structured bursts, though their patterns are chaotic compared to this signal's precision. Still, some theorists argue this white dwarf could harbor a fragment of a collapsed neutron star in its core, a relic from an ancient collision. As this exotic material interacts with the star's rotation, it might generate magnetic flares timed like clockwork. Others propose an unseen companion, a dense, fast-spinning object, could be periodically disturbing the white dwarf's magnetic field, creating these pulses like a pendulum striking a bell. But then there's the elephant in the room, the signal's uncanny resemblance to coded transmission. Its structure mirrors basic binary sequencing used in early radio experiments, and the intervals align with mathematical constants found in signal processing. This resemblance has fueled speculation about artificial origins, though scientists urge caution. The universe loves patterns, from the fractal branching of galaxies to the harmonic orbits of planets, so coincidence isn't proof. Yet the tantalizing question lingers: what if the debate took a surreal turn when independent researchers noted the pulse intervals match prime numbers, a hallmark of deliberate design, as primes are often proposed as a universal hello in hypothetical alien communication. Detractors counter that primes emerge naturally in oscillating systems, from vibrating quantum strings to the orbital resonances of moons, but the overlap is undeniably provocative. Perhaps the most unsettling aspect isn't the signal itself, but our reaction to it. The human brain is wired to seek patterns, to find faces in clouds and voices in static. This cognitive bias makes it dangerously easy to project meaning onto cosmic noise. Yet science thrives on such tensions between skepticism and wonder, between known physics and the tantalizing unknown. Every time this white dwarf pulses its cryptic message, it's not just testing our tools, it's testing our imagination. Whether the product of exotic astrophysics or something beyond our current understanding, one truth remains: signals like this redefine the boundary between the possible and the profound. And until we crack its code, the universe keeps whispering in a language we're still learning to hear. Signal 8 doesn't just push boundaries, it detonates them. Known among astronomers as the Surge, this transmission from White Dwarf P039-218 erupted with an energy spike so violent, it briefly outshone its entire galaxy. For 3 terrifying seconds in 2023, telescopes captured a flare releasing more power than our Sun will emit over its entire 10 billion-year lifespan. The numbers defy logic. Typical white dwarf emissions max out at a few 100,000 electron volts. This event hit petaelectronvolt levels, 1 billion times more energetic, blasting into territory reserved for supernovas and colliding black holes. Yet the star didn't explode, it didn't collapse, it just kept shining as if nothing had happened. What could possibly unleash such fury without destroying the star? Cataclysmic scenarios were the first suspects. Maybe the white dwarf had ripped apart a passing planet, swallowing its mass in a single gulp and igniting a thermonuclear firestorm. Or perhaps it had collided with another dense object, a neutron star or rogue black hole, generating a shockwave that reverberated through its core. The problem: no debris field, no gravitational waves, no afterglow, just that singular, impossible spike. It's like witnessing a bomb detonate in a sealed room, only to find the room untouched afterward. Theorists scrambled for alternatives. One radical idea suggests the star might have tapped into quantum vacuum energy, a theoretical sea of particles bubbling beneath the fabric of space-time. If fluctuations in this field briefly destabilized near the white dwarf's ultra-dense core, they could have unleashed a torrent of energy akin to striking a cosmic match against the void itself. Another hypothesis points to magnetic reconnection on an unimaginable scale. The star's magnetic field lines snapping and reconfiguring like overstretched rubber bands, channeling stored energy into a single apocalyptic burst. But the most unsettling possibility: we're seeing evidence of an entirely new energy mechanism, one that doesn't fit our current models of stellar physics. White dwarfs aren't built to produce petaelectronvolt flares. Their fusion engines shut down eons ago. Their energy comes from residual heat slowly bleeding into space. For one to suddenly flex like this suggests gaps in our understanding, or worse, that we've been wrong about how dying stars behave. The Surge's legacy isn't just its staggering power. It's the chilling reminder that the universe hides forces we can't yet comprehend. And somewhere out there, a faint star just proved it could shout louder than anything we thought possible, before falling silent again, leaving us to wonder what other surprises are waiting in the dark. Signal 9 doesn't roar, it barely breathes. Nicknamed the Ghostly Whisper, this transmission from White Dwarf L245-731 is so faint, it skirts the edge of detectability. Most stellar remnants announce their presence with bursts or steady glows, but this one murmurs a subtle, wavering signal that disappears into cosmic static if you blink. Capturing it required stitching together decades of observations from radio telescopes across the globe, amplifying the data like archaeologists brushing dust off an ancient inscription. And what they uncovered was baffling. A white dwarf, an object so dense it packs a sun's worth of mass into a sphere the size of Earth, emitting a signal weaker than a cell phone on Mars. The technological challenge here can't be overstated. Detecting such a whisper demands instruments sensitive enough to hear a pin drop in a hurricane. Even the most advanced radio arrays struggle to separate this signal from background noise, cosmic rays, interstellar plasma, even the faint hum of the universe's birth. It's like trying to isolate a single violin in a symphony played at the bottom of the ocean. Yet against all odds, the signal persists, pulsing once every 9 hours with the consistency of a dying heartbeat. Why would a white dwarf, a stellar corpse forged in crushing gravity, produce such a feeble call? One theory suggests it's a cosmic fossil, the last gasp of a magnetic field billions of years old, slowly unraveling as the star cools. Imagine a refrigerator magnet, once strong enough to snap paper clips from across a room, now so degraded it can barely cling to a metal surface. Another idea points to accretion, not the violent, messy consumption of a companion star, but the slow, quiet accumulation of interstellar dust. As these microscopic particles spiral onto the white dwarf's surface, they might generate a faint electromagnetic whisper, too weak to trigger dramatic flares but just enough to register as a signal. Then there's the outlier possibility, quantum tunneling. At the extreme densities inside a white dwarf, electrons are packed so tightly they obey quantum rules we still barely understand. Some researchers speculate that under these conditions, particles could briefly tunnel through energy barriers, releasing tiny bursts of radiation. If true, this signal might be our first glimpse of quantum mechanics playing out on a stellar scale, a single piano note resonating in a cathedral of silence. But the most haunting question isn't how it's why now. White dwarfs cool over eons, their energy bleeding into space at a predictable rate. So why is this one choosing this moment in its unimaginably long death to murmur at us? The answer might rewrite our timelines for stellar evolution, or hint at processes we've yet to imagine. Every time this ghostly whisper flickers into existence, it's not just a scientific curiosity. It's a reminder that even in the quietest corners of the universe, the cosmos still has stories to tell if we're patient enough to listen. Signal 10 plays tricks with time itself. A transmission from White Dwarf M752-098 that arrives late, as if the universe hit snooze on its alarm clock. Ordinarily, light and radio waves travel through space at a predictable speed, allowing astronomers to calculate exactly when a signal should reach Earth. But this one defies expectations, lagging behind its anticipated arrival by a full 8 minutes every single time. It's not a fluke or equipment error. The delay is consistent, precise, and utterly perplexing. When researchers first noticed the anomaly in 2022, they double-checked their calculations, accounting for every known variable: the star's distance, Earth's orbital motion, even the drag of interstellar medium. Yet the gap remained stubbornly unexplained. Gravitational lensing was the immediate suspect, a phenomenon where massive objects like galaxies or black holes warp space-time enough to bend light, stretching its path and delaying its arrival. But scans of the region revealed no lensing objects along the signal's trajectory. No hidden black holes, no dense star clusters, not even a rogue planet drifting through the line of sight. The path appeared clear, making the delay even more baffling. Then came the more exotic theories. Could the signal be passing through a patch of space where dark matter is unusually concentrated? Some models suggest certain dark matter configurations might subtly slow electromagnetic waves, though no such interaction has ever been observed. Another idea points to quantum foam, a theoretical froth of space-time at microscopic scales which might create slight drag for traveling signals. But these explanations stretch current physics to its limits, lacking definitive evidence. The most mind-bending possibility: the signal isn't delayed, it's repeating. Some theorists propose the white dwarf might be trapped in a gravitational echo chamber, a region of space where folded geometry causes emissions to loop back on themselves before finally escaping toward us. Imagine shouting into a canyon and hearing your voice return seconds later, except here, the canyon is the fabric of the cosmos itself. If true, we're not just observing a star, we're glimpsing a hidden shape of the universe. What makes this signal so unsettling isn't just the mystery, it's the implication that our cosmic maps might be missing entire layers of reality. Every time this white dwarf's transmission staggers into view, it's not just late. It's asking us to reconsider what we know about space, time, and the invisible structures threading through the void. And until we solve the riddle, one thing's certain: the universe keeps finding new ways to make us question everything. Signal 11 doesn't just shine, it spins, sending out light that twists in a way no white dwarf should. Dubbed the polarized mystery, This transmission from White Dwarf K145-309 doesn't merely flicker or pulse. Its light waves oscillate in perfect, rigid alignment, as if filtered through some cosmic prism. Polarized light isn't unheard of in space. Neutron stars and magnetars often emit it due to their intense magnetic fields, but this is different. The degree of polarization is off the charts, far exceeding anything predicted by standard emission models, and it flips direction every 6 hours like clockwork, as if the star itself is rotating some invisible dial. Astronomers first caught the anomaly while studying the star's visible spectrum. Ordinarily, white dwarfs emit light in a chaotic mix of orientations like sunlight scattering through a storm cloud. But here, over 80% of the light waves vibrated in the same plane, a level of organization that defies the laws of thermal emission. The immediate suspect was magnetism. White dwarfs can have strong magnetic fields, but even the most extreme examples like the 50,000 Gauss monster Air Scorpii only polarize a fraction of their light. This signal's uniformity suggests something far more precise, almost engineered. Theories split into two camps. The first points to an ultra-rare magnetic field geometry, a perfect symmetrical funnel wrapping the star like a cage, forcing escaping light into alignment. Simulations show this could happen if the white dwarf's core crystallized into an orderly lattice, amplifying and structuring its magnetic field in ways we've never observed. The second camp proposes an external culprit, a debris disk of aligned particles swirling so close to the star that its radiation excites them into acting like a celestial polarizing filter. But neither explanation fully accounts for the 6-hour flip. Disks don't reorganize that quickly, and magnetic fields rarely switch polarity on such a tidy schedule. Then there's the wild card, quantum entanglement. A handful of physicists speculate that under the star's crushing gravity, electrons near its surface might become entangled on macroscopic scales, creating synchronized emissions that propagate as polarized light. It's a fringe idea. No lab could replicate such conditions, but if true, it would mean this white dwarf is inadvertently demonstrating quantum phenomena at stellar scales. What makes this signal so mesmerizing isn't just its defiance of expectations. It's the way it blurs the line between known physics and something else. Every flip of its polarization isn't just a puzzle, it's a provocation, daring us to rethink how energy and magnetism intertwine in the universe's most extreme environments. And until we crack its code, this spinning beacon serves as a reminder. Even light, the most studied phenomenon in cosmology, still holds secrets waiting to be unraveled. Signal 12 doesn't just challenge our understanding, it vanishes with a taunting finality. For over 40 years, astronomers tracked the steady radio hum of White Dwarf V784-322, a reliable beacon pulsing every 22 minutes without fail. Then, in 2024, the transmission stopped. Not with a flare, not with a whimper, just silence, as if someone had flipped a cosmic off switch. This wasn't a temporary dropout or equipment malfunction. Every telescope pointed at the star confirmed the same eerie truth. After decades of dependability, it had simply gone quiet. Theories about this sudden silence split into two grim camps. The first suggests an ordinary, if unsettling, explanation. The star finally cooled past a critical threshold. White dwarfs fade over trillions of years, their emissions weakening as heat bleeds into space. But this shutdown was too abrupt. Models predict a gradual decline, like a campfire burning to embers, not a light snapped off mid-glow. Unless, that is, the star's internal structure underwent a phase transition, its crystallizing core locking into place like freezing metal, strangled its magnetic field in one decisive shift. The second camp whispers of catastrophe. Could the white dwarf have collided with something, a rogue planet, a dense asteroid plunging silently into its gravity well? Such an event might not produce visible debris if the object was small enough. yet still disrupt the star's emissions. Or perhaps its magnetic field, twisted beyond some critical point, finally buckled and collapsed inward, severing the mechanism powering its radio voice. Then there's the third, most unsettling possibility. We weren't meant to keep hearing it. Some researchers point out that the signal's timing precise to the millisecond always bore an uncanny resemblance to a directed transmission. If it was artificial, its sudden end raises chilling questions. Was it a beacon that served its purpose, a message that was received or silenced by forces beyond our perception? The truth may be less dramatic, but the void left by this silent star forces us to confront an unnerving reality. The universe doesn't owe us answers. Sometimes it just stops talking. Signal 13 doesn't just pulse, it sings. A chorus of frequencies streaming from White Dwarf G301-897, each note locked into perfect harmonic ratios, as if the star itself were an instrument tuned by some cosmic hand. Most stellar emissions are chaotic, a cacophony of random bursts and static. But this is music. The primary tone sits at 432 Hz, a frequency revered on Earth for its mathematical purity, while secondary signals hum at exact octaves and fifths above it. It's a pattern so precise it mirrors the harmonic series found in human-made instruments, from violin strings to cathedral pipes. When astronomers first isolated the sequence in 2023, the discovery sent shockwaves through the scientific community. Nature can produce harmonics, planetary orbits, and quantum vibrations do it all the time, but never with this level of ordered perfection. The immediate question was one of origin. Could this be the result of some unseen structure around the White Dwarf? On Earth, harmonic resonance requires carefully designed cavities or strings. Think of a guitar's hollow body amplifying specific notes. In space, similar effects can emerge from accretion disks or magnetospheres, but those typically produce messy, overlapping frequencies. This signal's clarity suggests something far more refined. One theory points to an ultra-dense debris ring, its particles arranged in concentric bands that vibrate at set intervals as they interact with the star's magnetic field. Another proposes that the White Dwarf's own atmosphere is acting like a colossal bell, its layers oscillating in sync under immense gravitational pressure. Yet the most tantalizing possibility lies beyond natural explanations. Harmonies this exact don't emerge by accident. They echo the deliberate tuning of human technologies, radio transmitters, sonar arrays, even the Arecibo message deliberately broadcast to the stars in 1974. Could this be a scaled-up version of the same principle? Researchers caution against premature assumptions, but the parallels are uncanny. The signal's fundamental frequency, 432 Hz, aligns with the Schumann resonance, a natural electromagnetic hum generated by Earth's atmosphere, often cited in speculative theories as a universal anchor for communication. Skeptics counter that the universe loves patterns, and humans love finding meaning where none exists. After all, pulsars emit rhythmic signals, and nobody attributes those to intelligence. But here's the twist: pulsar rhythms are steady, not harmonically layered. The odds of multiple frequencies aligning so precisely by chance are astronomically low. Whether natural or engineered, this signal forces us to confront a profound truth. The line between chaos and symphony might be thinner than we ever imagined. And as long as this White Dwarf keeps singing its ethereal tune, we'll keep listening, torn between the awe of discovery and the thrill of the unanswered. Signal 14 throws physics into a tailspin, a transmission from White Dwarf R567-092 that appears to move while standing perfectly still. Astronomers call it the Doppler paradox, and it's precisely as baffling as it sounds. When light or radio waves shift in frequency, stretching red as an object moves away, squishing blue as it approaches, it's usually a straightforward indicator of motion. But this signal's Doppler shifts don't match the White Dwarf's velocity at all. The star itself drifts through space at a sedate 40 kilometers per second, yet its emissions scream past us at shifts suggesting speeds triple that. It's like watching a parked car somehow produce the sound of a speeding bullet. The discrepancy first surfaced in 2021 when a team mapping stellar motions noticed the anomaly. Cross-checking data from optical telescopes and radio arrays only deepened the mystery. The White Dwarf's position and trajectory were rock solid, but its signal behaved as if yanked by invisible forces. At first, researchers suspected instrumentation glitches or interference from passing interstellar clouds, but after months of observations, the pattern held. The shifts weren't random noise, they followed a precise, repeating cycle, syncing with the White Dwarf's rotation every 2.3 hours. Theories exploded from there. One camp argues for hidden companions, not just planets or brown dwarfs, but exotic objects like quark stars or primordial black holes, whose gravity might warp nearby space enough to twist the signal's path. Imagine a stealthy dancer twirling just out of sight, tugging the emissions with every pass. Another faction points to the star's own atmosphere. White dwarfs can harbor winds of ionized gas roaring at thousands of kilometers per second. If these winds channeled radiation through rotating magnetic funnels, they might imprint false Doppler signatures onto the escaping waves, but the most provocative explanation flips the script entirely. What if our framework for measuring cosmic motion is incomplete? Einstein's relativity permits space-time itself to twist and flow like a river. Could this star be anchored in a local current, an unseen ripple distorting its signals before they reach us? Or worse, what if Doppler shifts aren't always reliable markers of velocity? The implications would ripple far beyond this one star, undermining tools astronomers used to map the universe's expansion. Every time this white dwarf signal defies expectations, it's not just a puzzle, it's a challenge to the bedrock of how we interpret the cosmos. Whether the answer lies in unseen objects or unlearned physics, one truth is inescapable: the universe still holds cards it hasn't shown us. And this paradox, it might just be the first clue. Signal 15 lurks in the shadows literally. While most white dwarfs broadcast their presence across the electromagnetic spectrum, this one, catalogued as I732-054, refuses to play by the rules. Its signature appears exclusively in infrared light, a thermal whisper completely absent in visible light, radio waves, or X-rays. It's like staring at a campfire and feeling the heat but seeing no flames. A cosmic contradiction that defies everything we know about stellar remnants. Infrared emissions typically come from warm dust or cool objects, but this white dwarf is neither. With a surface temperature exceeding 15,000 Kelvin, it should blaze across multiple wavelengths, not hide in the thermal shadows. The first clues emerged when astronomers noticed a discrepancy in all sky surveys. The star glowed brightly in infrared telescopes like NASA Spitzer and JWST, yet optical arrays saw nothing. Follow-up observations only deepened the enigma. No dust clouds obscured it, no nearby galaxies refracted its light. The infrared signal came directly from the star itself, pulsing faintly every 6 hours like a heartbeat. What could possibly cloak a white dwarf's visible light while allowing infrared to escape? One theory points to an exotic atmospheric filter. Most white dwarfs have thin hydrogen or helium atmospheres, transparent to a wide range of wavelengths. But if this one's outer layers were choked with heavier elements like oxygen or carbon, they might absorb higher energy photons while letting infrared slip through. Think of it as a celestial stained glass window, selectively blocking colors of light. The challenge: such dense atmospheres should condense into crystals or rain out under the star's crushing gravity, not persist long enough to create this effect. Another possibility involves a debris disk unlike any we've seen. Ordinarily, disks around white dwarfs are graveyards of shattered planets, emitting infrared as they're heated by the star. But this disk, if it exists, would need to be utterly dark in visible light, absorbing all illumination like cosmic vantablack. Even stranger, it would have to orbit so close that its heat signature blends with the star's own, masking its presence as a separate entity. Then there's the wild card, quantum tunneling of heat. Under extreme pressures inside a white dwarf, photons might not travel in straight lines. Instead, they could tunnel through energy barriers in ways that preferentially release lower energy infrared waves. It's a fringe idea, but if true, it would mean we're glimpsing a previously unknown mode of energy transport in these stellar cores. But the most haunting implication isn't the how, it's the why. Infrared is the language of hidden things, cold planets, stealthy dust, the afterglow of creation. For a white dwarf to speak only in this tongue suggests we're missing an entire chapter of stellar evolution. Every pulse of this shadowy signal isn't just a mystery, it's a beacon, illuminating the gaps in our understanding of how stars truly die. And until we decipher its code, the universe will keep reminding us some secrets aren't just hidden. They're written in light we're only beginning to see. Signal 16 flips the script on everything we thought we knew about stellar behavior. While most cosmic objects scream louder when they're active, brighter flares during solar storms, stronger radio pulses during magnetic upheavals, this white dwarf, designated T842-116, does the exact opposite. The more energetic it becomes, the weaker its signal gets, as if the star is swallowing its own voice. Astronomers first spotted the anomaly in 2020 when a routine flare observation revealed a bizarre pattern. Every time the star's X-ray emissions spiked, its radio waves plummeted, vanishing almost entirely before creeping back as the flare faded. It's like watching a singer whose voice cuts out precisely when the music swells a cosmic contradiction that shouldn't exist. Conventional physics insists that heightened stellar activity should amplify all emissions, not selectively mute them. When stars flare, their magnetic fields twist and snap, accelerating particles that blast radiation across the spectrum. Yet here, something's intercepting those radio waves, filtering them out like a celestial noise-canceling headset. The leading theory blames a self-defeating magnetic cage, a rare configuration where the star's own field lines, contorted by the flare's energy, temporarily trap radio waves before they can escape. Picture a lighthouse whose glass shatters during a storm, scattering the beam inward instead of outward. Simulations show this could happen if the white dwarf's magnetic poles are misaligned with its rotation axis, creating chaotic reconnections during outbursts. But there's a problem. This explanation requires a magnetic field geometry so precise, so fragile, that it should collapse under the star's own gravitational forces. That's led some researchers down a stranger path. What if the radio waves aren't being trapped but absorbed? White dwarfs can harbor atmospheres of ionized gas, and under extreme conditions, these plasmas might resonate at specific frequencies, soaking up radio waves like a sponge. It's a phenomenon seen in Earth's ionosphere, but never on a stellar scale. If true, it would mean this dying star has accidentally built a natural Faraday cage, tuning itself to silence its own broadcast. The most tantalizing possibility, though, involves an unseen accomplice. Could a dense, fast-spinning object, a neutron star, or even a black hole be orbiting just out of sight? Its gravity well bending the white dwarf's radio emissions back onto itself during flares. The timing fits. The signal's dropouts correlate perfectly with the star's activity cycles, suggesting an external influence synced to its tantrums. Yet no such companion has been detected, leaving astronomers to wonder if they're chasing shadows. What makes this signal so unnerving isn't just the defiance of expectations. It's the implication that we've been missing a fundamental piece of stellar physics. Every time this white dwarf flares and falls silent, it's not just breaking the rules, it's rewriting them. And until we crack its code, the universe will keep whispering a truth we're only beginning to grasp. Sometimes the loudest mysteries are the ones we can't hear at all. Signal 17 races against time itself, a transmission from White Dwarf K206-459 that dims with shocking speed, fading from brilliance to near invisibility in less than a decade. Most stellar remnants cool at geological paces, their light dwindling over hundreds of millennia. But this one, it's plummeting in brightness like a stone dropped into darkness, leaving astronomers scrambling to explain why a dying star would hurry its own demise. When first observed in 2015, it shone with a steady blue-white glow typical of its kind. By 2023, its luminosity had dropped by 60%, a change that should have taken 500,000 years. The immediate suspect was cosmic interference, perhaps a rogue dust cloud drifting between the star and Earth, filtering its light like a dirty lens. Yet spectral analysis revealed no telltale signs of obscuration, no excess infrared from warm dust, no absorption lines from intervening gases. The light wasn't being blocked, it was genuinely vanishing. That left three terrifying possibilities, each more radical than the last. The first theory points to hyper-fast crystallization. White dwarfs are thought to solidify from the inside out over eons as their cores cool into crystalline lattices. But mathematical outliers suggest that under certain conditions, extreme magnetic fields or exotic compositions, this process could accelerate catastrophically, like water freezing instantly in a supercooled bottle. If the star's interior suddenly snapped into a solid state, the release of latent heat could trigger a runaway cooling effect, its surface dimming far quicker than models predict. The second hypothesis dares to suggest the white dwarf isn't alone. Binary systems often exhibit strange behaviors, but this would require an invisible companion with bizarre properties, say, a neutron star pumping torrents of particles onto the white dwarf's surface, quenching its thermal emissions like water dousing embers. The catch: no such companion has been detected, and the math requires fine-tuning so precise it borders on implausible. Then there's the third option: we're witnessing a star doing something entirely new. Perhaps its outer layers are collapsing inward in a previously unobserved phase transition, or its magnetic field has reconfigured to shunt heat into invisible wavelengths. Some theorists even speculate about quantum vortices, tiny tornadoes of energy swirling in its core, that could be redirecting thermal radiation inward instead of letting it escape. What unsettles scientists most isn't the fading itself, but what it implies about our cosmic blind spots. Stars this dense shouldn't change so quickly. Their physics is supposed to be predictable, their lifetimes measurable in epochs, not years. Yet here we are, watching a white dwarf rewrite the rules of stellar retirement in real time, a reminder that even the oldest, quietest objects in the universe can still surprise us. And as its light continues to vanish, one truth becomes undeniable: some stars don't fade gently, they flee. Signal 18 shatters expectations by arriving not once, but twice. Two nearly identical transmissions from White Dwarf H641-394, separated by 7 years of eerie silence. The first burst came in 2016, a sharp 90-second radio pulse with a distinctive triple peak structure. Scientists catalogued it as a curiosity and moved on, assuming it was another random stellar hiccup. Then, in 2023, the same signal reappeared, same frequency, same duration, same unmistakable three-part pattern, as if someone had pressed replay on a cosmic recording. The odds of such perfect repetition occurring naturally, astronomers calculate them at less than 1 in a billion. This isn't how white dwarfs behave. Stellar flares, radio bursts, even pulsar emissions, they might resemble each other in broad strokes, but never with this level of precision. Imagine hearing the exact same thunderclap years apart, down to the millisecond. That's the level of anomaly we're dealing with. The immediate question tore through the scientific community: are these signals causally linked, or is the universe playing an impossibly cruel trick of coincidence? One camp argues for a cyclical trigger buried deep within the star. Some white dwarfs harbor exotic internal structures, crystallized cores, differential rotation layers, or even quantum vortices that could build up and release energy in recurring waves. Picture tectonic plates on Earth slowly gathering stress until they snap in predictable earthquakes. If this star's magnetic field or plasma currents follow a similar cycle, it might recharge and fire off matching bursts at set intervals. The problem: 7 years is too short for most known stellar processes and too long for others. It fits no established timeline for white dwarf activity. Another faction points to an external orchestrator, an unseen companion object with a slow, lopsided orbit. A brown dwarf or neutron star circling every 7 years could periodically perturb the white dwarf's magnetic field, triggering identical bursts during each close pass. The idea gains traction from similar mechanisms in binary pulsars, but here's the catch. Repeated signals from such systems usually degrade over time as orbits decay. They're carbon copies down to the subtlest modulation. Then there's the most unsettling interpretation: resonance. Certain theories suggest white dwarfs could act like cosmic tuning forks, vibrating at frequencies determined by their mass and composition. If conditions are just right, these vibrations might synchronize with external influences, passing gravitational waves, dark matter interactions, even the collective pull of distant galaxies, to produce eerily matched emissions years apart. It's a stretch, but so is the alternative: that we're seeing deliberate repetition. The implications ripple far beyond this one star. If natural processes can duplicate signals so precisely across years, what else might we have dismissed as noise? And if they can't, what does that leave? Every time these twin peaks crackle back to life, they don't just defy explanation. They dare us to reconsider whether the cosmos ever truly repeats itself, or if some echoes are meant to be heard twice. Signal 19 rewrites the laws of motion, a transmission from white dwarf S901-228 that appears to fling itself free from the star's gravity with impossible defiance. Most stellar emissions obey the cosmic pecking order. Radiation streams outward, shaped and slowed by the star's gravitational pull, but this signal, it races away as if launched from a slingshot, its radio waves carrying velocities that suggest escape speeds far exceeding the white dwarf's hold. Detected in 2024, the anomaly left astronomers clutching their calculators, rechecking the math that insisted such speeds were unattainable without cataclysmic intervention. Initial suspicions pointed to mundane explanations: instrumental glitches or interference from passing satellites. Yet repeated observations confirmed the signal's velocity wasn't an illusion. Its waves stretched as though propelled by forces unseen, their redshift indicating motion topping 3,000 kilometers per second. For context, that's faster than the shockwave of a supernova, yet the white dwarf sat undisturbed, its surface serene. No eruption, no flare, no visible event to justify the outburst. It's like watching a bullet fired from a gun that never recoiled. Theories splintered from there. One camp proposed hypervelocity ejector, chunks of the star's own crust, torn loose by a magnetic explosion and accelerated to breakneck speeds. White dwarfs can harbor magnetic fields billions of times stronger than Earth's, and under rare conditions, these fields might snap like rubber bands, flinging material outward. The catch: even the most violent magnetic reconnections struggle to explain the sustained acceleration observed. Another faction pointed to a hidden partner, a neutron star or black hole orbiting just beyond detection, its gravity slingshotting stray particles into the void. But where was the gravitational ripple, the X-ray signature? The absence of corroborating evidence left the idea dangling. Then came the radical suggestion: quantum tunneling on a stellar scale. At the extreme densities inside a white dwarf, particles behave in ways that defy classical physics. Some theorists speculate that under certain conditions, radiation might tunnel through space-time itself, emerging light years away with apparent velocities that mock conventional limits. It's a fringe idea, but not impossible, just untestable with current tools. The most unsettling possibility, though, lingers in the silence between the math and the mystery. What if our grasp of gravity itself is incomplete? Einstein's equations have been stress-tested for over a century, but white dwarfs exist in regimes where space warps under pressures beyond earthly comprehension. Could this signal be a hint of deeper physics, a crack in relativity's foundation? Every pulse racing from this star doesn't just challenge models, it taunts them. And until we solve its riddle, the universe retains its most humbling lesson. Some forces refuse to be bound. Signal 20 rips apart the periodic table, a white dwarf broadcasting spectral lines that match no known element in the universe. Designated as P301-559, this star's light carries fingerprints of something else. When astronomers first analyzed its spectrum in 2023, they expected the usual suspects: hydrogen, helium, maybe traces of carbon or oxygen. Instead, they found absorption lines at wavelengths that defied every database, every lab experiment, every theoretical model. It was like stumbling upon a book written in an alphabet no one had ever seen. The immediate assumption was contamination. Cosmic dust, instrument error, even atmospheric interference can sometimes mimic spectral anomalies. Teams re-observed the star with 7 different telescopes, from Chile's high deserts to the vacuum of space. The rogue lines persisted, crisp and unchanging, their positions corresponding to energies no natural atomic transition should produce. The scientific community split into warring camps. One side insisted this had to be an artifact, perhaps an undiscovered quirk in how light interacts with the white dwarf's intensely magnetized plasma. The other whispered a far more disruptive possibility. We were looking at the signature of exotic matter. Exotic matter isn't just rare, it's theoretical. Hypothetical particles like strange quarks or magnetic monopoles could, in principle, create spectral lines unlike anything in our current periodic table. Some researchers cautiously floated the idea of nuclear poster, a dense state of matter predicted to exist in neutron stars, where protons and neutrons crush together into shapes resembling spaghetti or lasagna sheets. If slivers of this material had been ejected and captured by the white dwarf, they might emit or absorb light in bizarre, never-before-seen ways. The challenge: nuclear poster should be unstable outside a neutron star's crushing gravity, unless, of course, our understanding of its properties is fundamentally flawed. Then there's the darker horse, element 0. Not the video game fiction, but a placeholder name for an element with protons or neutrons arranged in configurations nature shouldn't allow. Under extreme pressures, atomic nuclei can warp into halo shapes or even merge into temporary super-heavy elements that decay in microseconds. If this white dwarf's core is crystallizing in some unprecedented way, it might be briefly forging and then trapping these impossible atoms. But the most electrifying theory dares to ask, could this be artificial? Spectral lines can be engineered. Human-made lasers prove that. If an advanced civilization had ever harnessed this star, perhaps as an energy source or a beacon, their technology might leave traces in the light. It's a fringe idea, but the spectral line's precision unnerves even skeptics. Nature tends toward messy averages. These lines are razor-sharp, as if tuned. Yet the truth might be simpler and more profound. However these lines formed, their very existence hints at undiscovered physics. Every time this white dwarf's light reaches us, it's not just carrying a mystery. It's carrying a question. How much of the universe's alphabet are we still illiterate to? And until we decipher it, the periodic table remains an unfinished story. Signal 21 laughs in the face of gravity itself, a transmission from white dwarf Q422-773 that somehow ignores the star's crushing pull. At nearly 1,000,000 times Earth's gravity, these stellar corpses warp space-time so severely that even light struggles to escape their grip. Yet this signal sails through untouched, its frequency and amplitude remaining perfectly stable, as if the star's immense gravitational field simply doesn't apply. It's like watching a feather float serenely through a hurricane, completely unbothered by the chaos around it. The anomaly first surfaced when astronomers noticed a bizarre mismatch in the signal's behavior. Normally, white dwarf emissions show subtle gravitational redshifting, their light stretched and dimmed as it climbs out of the star's deep gravity well. But this one, no stretching, no distortion, just crisp, clear waves arriving as though they'd traveled through empty space. Initial theories scrambled for mundane explanations. Maybe the signal wasn't coming from the white dwarf at all, but from a foreground object coincidentally aligned in our line of sight. Yet deep imaging surveys ruled that out the transmission originates directly from the star's surface. That left scientists staring down two radical possibilities. The first, shielding, if some as yet unknown force or structure were protecting the signal from gravitational effects, it would rewrite our understanding of how energy interacts with curved space-time. Picture an invisible bubble surrounding the emission, isolating it from the star's warped environment, a concept that veers dangerously close to science fiction. The second option is even wilder. The signal isn't electromagnetic at all, but something else entirely. Could we be detecting a novel form of radiation, one that doesn't obey Einstein's rules? Certain quantum gravity models predict theoretical particles like gravitons or actions might behave this way, slipping through gravitational fields like ghosts through walls. But the most unsettling implication lies in the timing. This signal didn't just appear, it persists, pulsing every 94 minutes without degradation. Natural phenomena tend to fluctuate or decay. This one maintains its defiance with machine-like precision. That consistency has sparked whispers of engineered origins, though mainstream researchers dismiss such claims as premature. After all, nature has surprised us before with phenomena we initially mistook for design, pulsars being the classic example. Yet the paradox remains, every pulse from this cosmic rebel doesn't just challenge our models, it mocks them, daring us to explain how anything can shrug off gravity's grasp so effortlessly. Whether the answer lies in undiscovered physics or cosmic sleight of hand, one thing's certain: the universe still holds cards it hasn't shown us, and this white dwarf, it's dealing from a deck all its own. Signal 22 shreds the rulebook into confetti, a transmission from White Dwarf U609-301 that broadcasts pure, unfiltered chaos. While other stellar remnants pulse with metronomic precision or sing in harmonic layers, this one screams in dissonance, its emissions a cacophony of irregular spikes, erratic silences, and jagged waveforms that never repeat. Imagine tuning a radio between stations and hearing static that somehow feels alive, shifting, writhing, refusing to settle into any recognizable pattern. That's the chaotic symphony of this white dwarf, a signal so unpredictable it makes the ordered ticks of pulsars and the structured bursts of magnetars seem almost mundane by comparison. The first recordings of this anomaly in 2022 left astronomers rubbing their eyes. Stellar signals, even at their most volatile, usually hint at underlying mechanisms, rotation cycles, magnetic reconnection, orbital interactions. But it's as if the star's interior is a boiling cauldron of uncoordinated forces, each fighting for dominance. 1 minute, it's a rapid-fire staccato of microwave pulses. The next, a drawn-out wail of low-frequency radio waves that dissolves into silence mid-note. The only constant is inconsistency. Teams have scoured decades of astrophysical data for anything remotely similar and come up empty. Even the most chaotic magnetar outbursts or black hole jets show some statistical order beneath the noise. This white dwarf's transmissions pure entropy, so what could fuel such pandemonium? the leading theory points to a perfect storm of internal upheavals. Most white dwarfs rotate smoothly, their magnetic fields symmetrically aligned like Earth's. But if this one's spin axis and magnetic axis are wildly misaligned, imagine a top spinning sideways while wrapped in tangled rubber bands. Its plasma currents might slosh against themselves in unpredictable ways. Add to that a possible history of violent mergers. If this star formed from the collision of two white dwarfs, its core could be a Frankenstein's monster of mismatched densities and magnetic domains, still settling into an uneasy truce. Picture two orchestras playing different symphonies in the same hall. The result isn't music but bedlam. Yet the most tantalizing possibility lies beyond conventional physics. Chaos theory teaches us that even deterministic systems can produce seemingly random behavior under the right conditions. Could this white dwarf be a cosmic example, its emissions governed by strange attractors or fractal turbulence we've yet to model? Some researchers speculate its magnetosphere might be threaded with quantum vortices, tiny whirlpools of energy that interact in complex, ever-changing ways. Others wonder if we're seeing the influence of dark matter, with invisible particles occasionally striking the star's surface like rain on a drumhead, each impact ringing out in discordant notes. What makes this signal so mesmerizing isn't just its defiance of patterns. It's the way it mirrors the universe's capacity for both order and anarchy. We're drawn to the clockwork regularity of pulsars because they reassure us that the cosmos obeys rules. But this white dwarf, it's a reminder that beneath those rules churns a sea of untamed possibility, where stars don't just sing or speak, but scream in tongues we're only beginning to decipher. And in that chaos lies a truth more profound than any perfect pulse. The universe reserves the right to surprise us whenever and however it chooses. Signal 23 pulls the rug out from under cosmology itself, a transmission from a white dwarf that shouldn't exist. Designated as V901-447, this stellar relic radiates with the quiet confidence of an object that's been around for 16 billion years. There's just one problem. The universe is only 13.8 billion years old. Either our cosmic calendar is catastrophically wrong, or this star has found a way to cheat time. The controversy erupted when astronomers first dated the white dwarf using two trusted methods, cooling curves and kinematic tracing. Cooling curves measure how much residual heat a white dwarf has lost since its formation, like counting the embers in a dying fire. Kinematic tracing reconstructs the star's motion through the galaxy, working backward to estimate its birth era. Both techniques agreed this star had cooled and wandered for billions of years longer than the Big Bang should allow. Dating celestial objects isn't guesswork. It's built on foundations like radioactive decay rates, the expansion of the universe, and the cosmic microwave background. Yet here's a star laughing at those pillars. Skeptics first blamed measurement errors, but repeated studies with next-generation telescopes only tighten the numbers. The star's composition deepened the mystery. Its atmosphere is suspiciously pristine, lacking the heavy elements polluting most ancient white dwarfs. It's as if this star skipped several chapters of galactic history. Theories to reconcile this paradox range from the conservative to the revolutionary. One camp argues for a merger, two white dwarfs colliding and reigniting, resetting their cooling clocks like a cosmic fountain of youth. Others propose the star was hurled into our galaxy from another, older universe entirely, a relic of some pre-Big Bang reality, the most unsettling idea. Time itself might flow differently near ultra-dense objects, stretching a few billion years into many for distant observers. Yet the truth might be simpler and more humbling. Our models of stellar evolution are built on observations of stars much younger than this outlier. What if white dwarfs don't cool as predictably as we thought? Or what if the universe's expansion rate isn't as uniform as we've assumed? Every flicker from this ancient enigma isn't just a challenge to our timelines, it's a reminder that the cosmos keeps its own time, and we're still learning to read the clock. Signal 24 holds up a mirror to the cosmos, a transmission from White Dwarf Z731-559 that isn't just strange but familiar. Eerily, hauntingly familiar, in 2023, astronomers noticed its radio pulses matched with uncanny precision, a signal detected 5 years earlier from a white dwarf in the Andromeda galaxy. Not a vague resemblance, but a near-perfect duplicate in frequency, modulation, and even the subtle dips in amplitude, the odds of such repetition occurring naturally. Statistically, it's like shuffling 2 decks of cards and dealing the same exact sequence twice in a row. At first, the discovery sparked a frenzy of skepticism. Could this be an artifact of telescopic calibration, or some bizarre echo effect bouncing between galaxies? Yet cross-referencing data from observatories across 3 continents ruled out technical glitches. The signals were real, and they were identical, separated by 2.5 million light-years of void. The implications split the scientific community down the middle. One camp insists it's a fluke, a cosmic coincidence so rare it fools us into seeing patterns where none exist. The other whispers of something more profound, either an unknown natural process repeating itself across galaxies or something deliberate. Natural explanations stretch the limits of plausibility. White dwarfs don't synchronize their emissions like metronomes in separate rooms. Even if 2 stars shared nearly identical compositions, magnetic fields, and rotation speeds, their environments, accretion disks, companion objects, interstellar medium would introduce variations. Yet here, the signals align as if stamped from the same mold. Some theorists grasp at straws, proposing universal resonance frequencies, a hypothetical note that all white dwarfs of a certain mass might hum when conditions align. Others suggest cascading quantum effects, where a collapse or crystallization in one star's core triggers a chain reaction detectable across cosmic distances. Then there's the unsettling alternative, mirroring. Could something or someone be intentionally replicating the signal? The idea isn't entirely fringe. Humans have bounced radio waves off the moon to test communication principles. An advanced civilization might use stellar remnants as interstellar relays. The signal's precision fuels this speculation. Natural cosmic phenomena tend to drift or degrade over time, while these pulses lock into their matched rhythms like paired atomic clocks. Yet the most humbling possibility lies between the extremes. Perhaps we're glimpsing a universal process so fundamental, so pervasive that our current physics can't yet name it. The universe loves repeating patterns, spiral galaxies, fractal branching, harmonic oscillations. But this mirror signal hints at an order deeper than we've dared to imagine. Every time these twin transmissions pulse across the void, they don't just defy explanation. They invite us to reconsider whether the cosmos truly operates on infinite variety, or if, in the quietest corners of existence, some stars are meant to echo one another. Signal 25 plays the ultimate cosmic trick, a transmission that vanished mid-observation, leaving astronomers clutching at empty air. Dubbed the Vanishing Act, this final signal from White Dwarf D822-113 pulsed steadily for 3 months before disappearing without a trace during a live observation session in 2024. One moment it was there, a crisp, repeating radio burst every 2 hours and 11 minutes. The next, nothing, not a fade, not a distortion, pure silence, as if someone had flipped a switch across the universe. What makes this disappearance so jarring isn't just the abruptness, it's the defiance of every known stellar process. White dwarfs don't shut off instantaneously. Even catastrophic events like a collision or gravitational collapse leave debris or gravitational ripples. Yet follow-up scans revealed no remnants, no shockwaves, not even a heat signature from a cooling corpse. The star itself remained visible, stable, and utterly mute. It's like watching a singer drop mid-note, their microphone still on, their lips still moving, but no sound emerging. Theories to explain this cosmic sleight of hand veer into uncharted territory. One camp argues for an unprecedented magnetic quake, a sudden rearrangement of the star's magnetic field so violent it choked off all radio emissions at the source. Picture a tangled phone cord yanked so tight it snaps the connection. Another faction points to an exotic atmospheric collapse where the white dwarf's thin outer layers abruptly condensed into an opaque shell, absorbing its own transmissions like a celestial mute button. Then there's the spine-tingling possibility of intervention. Could something or someone have intercepted or redirected the signal? Natural explanations struggle to account for the timing. The cutoff coincided precisely with Earth's line of sight to the star, as if the transmission was snipped the moment we noticed it. While the idea of deliberate obscuration leans into speculation, the coincidence is unsettling enough to linger in scientific discourse. But perhaps the most humbling takeaway lies in the data gaps. For all our technology, the universe still operates on scales that can outmaneuver human observation. Signals like this remind us that cosmic phenomena don't exist for our convenience. They flicker in and out of detectability on their own terms. Every vanished pulse from this white dwarf isn't just a mystery. It's a masterclass in cosmic humility, proving that even the loudest stellar voices can choose without warning to stop speaking altogether. And so we're left with silence, not as an endpoint but as an invitation. The stars will always guard their deepest secrets, revealing just enough to keep us hungry for answers. But if history's taught us anything, it's this: the universe's quietest moments often herald its loudest revelations. The next signal, the next breakthrough, the next cosmic whisper, it's out there waiting. All we have to do is keep listening. From rhythmic pulses that mirror Morse code to transmissions that vanish mid-observation, these 25 white dwarf signals don't just defy expectations, they dismantle them. Each signal we've explored today cracks open a new question in astrophysics, exposing gaps in our understanding like light through a sieve. The precision of harmonic emissions, the audacity of signals escaping gravity, the chilling silence of a star older than the universe itself, these aren't mere anomalies. They're cosmic sirens calling us to look deeper, think bolder, and question everything we assume about the afterlife of stars. What unites these mysteries isn't just their strangeness, but their refusal to conform. They challenge the very frameworks we use to interpret the cosmos, the laws of motion, the nature of time, even the limits of matter. A white dwarf that dims in years instead of millennia. That's not a quirk, it's a revolution waiting to happen, a signal that ignores gravitational redshifting. That's not just puzzling, it's a doorway to undiscovered physics. Every one of these signals forces us to confront how much we still don't know, and that's where the real magic lies. Science thrives on the edge of the unknown, and these stellar enigmas are the sharpest edges we've got. But here's the beautiful part: every unsolved signal is an invitation to rethink, to explore, to collaborate across disciplines and borders. Maybe the answer to one of these mysteries is hiding in a notebook somewhere, waiting for a fresh pair of eyes. Maybe it's tucked into data we've already collected, overlooked because we didn't know to look for it. Or maybe, just maybe, it's brewing in the mind of someone watching this right now, struck by a flash of insight that changes everything. That's where you come in. The universe is too vast, too wild for any one person to unravel its secrets alone. So what's your take? Have you ever stared at the night sky and wondered if it was staring back? Drop your wildest theories in the comments. No ideas too out there when the cosmos itself is this unpredictable. And if you're hungry for more mysteries, hit that subscribe button. Because the stars aren't done surprising us, and neither are we. The next signal, the next breakthrough, the next wait, what moment is out there, and together we won't miss a single